So in this session, we are going to study a program for plotting double-sided spectrum. Last time we had seen how to use the fast Fourier transform function in order to plot the spectrum, but that was plotting only positive frequency part of the spectrum. We now want to study the modified program which will plot both sides of the spectrum for positive frequencies as well as negative frequencies. All right. So before we study the program, we first study a function what is called as the FFT shift, and we'll see what it does, and then we'll look at the program. So first of all, let's assume that x is some function of n. N as usual is a discrete variable. Now you use the FFT function to find the discrete Fourier transform of x and store it in capital X. Then what you do is you use FFT shift function and store the result in y. So the input parameter to the FFT shift is the x array that is returned by the FFT function. Now what this particular function does, in order to understand, let us first of all assume that x contain these elements x0, x1, x2, x3, x4. These basically represent the frequency spectrum of x. And in this case, we are assuming that n is equal to 5. Then what the FFT shift will do, it will actually shift this x0 to the center of the sequence and then swap x3, x4 with x1, x2. So when FFT shift is performed, y will look like this. Y x0 comes at the center, x3 and x4 are swapped with x1 and x2. So you get x3, x4, x0, x1, x2. So that is what the FFT shift function does. Basically, the zero frequency has been brought to the center. So this will now represent the negative frequency components, and these two will represent the positive frequency components. So in order to plot the spectrum, you have to now adjust k appropriately. So k, which is the frequency index, when you use FFTX and plot the spectrum, we simply use the positive frequency index 0, 1, 2, 3, 4. But since we now want to see the double-sided spectrum, this needs to be adjusted. So how do we adjust it? It must range from some negative value to some positive value. So what are these values? So if n is an odd value, in this case n is equal to 5, in that case k ranges from minus n minus 1 by 2 to plus n minus 1 by 2. So in this case n is equal to 5, so 5 minus 1, 4 divided by 2, so it ranges from minus 2 to plus 2. That means k will have values minus 2, minus 1, 0, 1 and 2. So when k is equal to 0, you get x0. When k is equal to 1, you get x1. When k is equal to minus 1, you get x4. So when you plot y as a function of k, you will see the double-sided spectrum. Now you can either plot the frequency index on the x-axis, or you can plot the digital frequency, which is k by n. So in this case, since n is equal to 5, minus 2 by 5, so that is minus 0.4. This is minus 1 by 5, so that is minus 0.2. This is 0, this is 0.2, and this is 0.4. So this will mean that at minus 0.4, you will get x3, minus 0.2, you will get x4, at 0, you will get x0, and so on. All right. Now, this is the formula you use for finding the k array when n is odd. But suppose n is even. So let us take a specific example in which n is equal to 6. So you have got 6 components in the spectrum here: x0, x1, x2, x3, x4, x5. So when you perform the FFT shift, what will happen? This x0 will come at the center. So it will come after x1, x2, x3. And then these x1, x2 and x3 will be swapped with x4, x5. So in this case, y that you will get x3, x4, x5, and then x0, x1, x2. This is what you will get. And in this particular case, the array k is obtained by this particular equation, minus n by 2 with a default increment of 1 up to n by 2 minus 1. So in this case, n is equal to 6. So this is minus 3 and this will go to 2. So from minus 3, it will go to 2. So it will be minus 3, minus 2, minus 1, 0, 1, 2. That means at k equal to minus 3, you have x3. K equal to minus 2, you have x4. K equal to minus 1, you have x5 and so on. And this can be converted into digital frequency also by dividing by n. So you divide by 6. So this becomes minus 3 by 6. So that is minus 0.5. This is minus 2 by 6. So that is minus 1 by 3. That's minus 0.33 and so on. So this is the digital frequency. So now when you plot k by n versus y, or rather y versus k by n is on the x-axis, then you will get a double-sided spectrum when n is even. Alright. So these tell you the basics about what the FFT shift function does. So let us now look at the program. So most of the program that we studied in the last session, most of it is like this. Only at couple of places you have to insert some of the statements. So this n equal to 5, you generate the n index, you generate the k index. Remember, this is the time index, this is the frequency index. Then k1 equal to 1, n1 equal to 5. You generate your x again. This is the fundamental component, this is the second harmonic. This is the amplitude of 1 and this is the amplitude of 0.5. Then you calculate XTF1 by using the FFT function. Once you have this, you are now ready to use the FFT shift function, which we have studied. So I have deliberately written this in red to tell you that most of the rest of the program remains as it is, except the statements which are in red are the ones that we insert in order to plot the double-sided spectrum. Okay. So once you have done this, then the rest of this again usual. For Fourier series, you divide by n. Then you calculate the magnitude by using the absolute function. Then you calculate the phase by using the angle function. Then you make the angle 0 whenever the absolute value of XTF is less than 1% of the maximum value of the XTF. Now here, these are the extra statements that you require because you have to adjust the K array appropriately for double-sided spectrum. Mind you, when you did this calculation, your K was changing from 0 to n minus 1. But after the FFT shift, you have centered the 0 frequency, therefore K has to be changed appropriately. So when n is even, so that condition is checked by if mod of n2 is equal to 0, then you use this value of K, this equation for K for getting the K array, or if it is odd, you use this equation. The rest of it is plotting. So you plot stem K by n x, so that is the magnitude spectrum, and then you plot stem K by n xa, that is the phase spectrum. So let us take a look at the output. This is how it will look. You can see that in this case, K by n is minus 0.4, it's minus 0.4 here, then minus 0.2, 0, plus 0.2 and plus 0.4. And at these values you get, so at minus 0.2 you get 0.5. Remember, this is a double-sided spectrum. So the original fundamental amplitude, which is 1, becomes 0.5. So this is at both the frequencies, positive 0.2 digital frequency and negative 0.2. And the second harmonic, as we have seen, is half this amplitude, so it is 0.25. And you can see therefore that the amplitude spectrum is a even function of frequency, whereas the phase spectrum is the odd function of frequency. So again you get minus pi by 2 for both these frequencies because both of them are sine waves, and phase spectrum is an odd function of frequency. So if this is minus pi by 2, you get plus pi by 2 here. Again this is minus pi by 2, so you get plus pi by 2. So that is for n equal to 5. Alright, similarly, if you run the program by modifying n to the value of 6, then you will get K by n, that's minus 0.5, minus 0.33, etc. So minus 0.5, minus 0.33, then minus 0.166, then 0 again, and so on. Again, you can see that your amplitude spectrum is an even function of frequency and phase spectrum is an odd function of frequency. So in this particular session, we have seen the use of FFT shift function, which enables you to plot the double-sided spectrum. And that's all in this session.